Well, there are requirements for sound pressure level from technical installations in buildings. This is typically in the form of an A-weighted sound pressure level. There are national guidelines as well as international standards that describe methods for measuring sound pressure from technical installations in buildings. It is, however, problematic only to classify a sound source based on a sound pressure measurement. That's because the room size, the position of the sound source and room acoustics, they all influence the result. And if you measure the same sound source in two vastly different rooms, you may get quite different results. If a manufacturer is to guarantee a sound pressure level, he also has to set requirements for the installation as well as the room properties. If you'd wish to compare two sound sources, it would be more correct to measure the radiated sound power instead. That's because this will be completely independent of the surrounding properties. One of the problems with this is that both sound pressure and sound power are measured in decibels. The point here is that the decibel is always relative to some reference value, and for sound pressure it's 20 micropascals, while for sound power it's 1 picowatt. And this is where laypersons often make the error that they compare decibels for sound pressure and sound power, which is not possible without a conversion. At Airmaster, we typically perform measurements of sound pressure in rooms with our units installed in an appropriate room using national guidelines as well as ISO 16032. In addition, in recent years, we have been measuring sound power from some of our newer units, however, using a very tedious intensity procedure. However, last year we inaugurated our new test center, which combines a flow measurement facility with a reverberation chamber. And this enables us to measure both flow and sound power concurrently. And this will enable us to get a lot more sound power measurements across the development process and also across a greater span of operating points than was previously possible. It has quite a significant impact on the final result. The sound from our decentral ventilation units is dominated by the radiation from the inlet and extraction ducts. And this is because we've been very careful with the construction of the cabinets. We have ensured that the sound being radiated from internal noise sources through the cabinet walls is not dominating the final result. The materials and wall thicknesses are chosen such that strong sound is not radiated through the cabinet walls in a way that it influences the final results. This often means that the cabinets are made from steel with appropriate damping materials applied, and in critical locations we are employing sandwich construction and double-plated walls. The fluid mechanics are of great importance to how the sound from a ventilation unit is experienced. If you fail to optimize the inlet nozzles, it may result in a high frequency or broad spectrum noise component that can be experienced as a hissing sound. Also, if you fail to optimize the inflow to the fans or try to redirect the airflow in a confined space, turbulence may arise, and this may give rise to a low frequency rumbling sound. We pay great attention to avoid this. In the AMX4, we are, in addition to two fans, housing a compressor inside the cabinet. First, we had to attenuate the sound being radiated through the cabinet walls using our past experiences. However, with regards to the compressor, we had to develop a compact vibration damper to avoid the vibrations from propagating to the cabinet in the first place. It's extremely important that you're not subjected to noise that over a prolonged period may give rise to annoyance. Otherwise, you may find it hard to concentrate, and even at the end of the day you might feel stressed or tired. Thus, it's an extremely important parameter where we strive to be the best.